Okay. Hi, everyone. Hopefully, it's working. Yes. So, welcome to our next lecture, one of the very last lectures about physical and database modeling. Today, we want to jump into a new topic, still database, but we try to bridge the gap towards the physical interpretable situation to get more interpretation into what we are doing. So, if you remember one of our last lectures, we talked about discrete time systems. We have a set of sample data and said, okay, use the sample data to deduce the discrete time system. But if you remember your lectures at the very beginning of your control engineering career, you might, well, hopefully it's still working. You might realize that, well, discrete time systems are nice, but always a little bit strange, because if you look at the Z transform things and all the parameters, they do not really relate to what you know from physical systems. So you get additional zeros which are not present, and in the continuous time system due to the sampling process. You have these exponential functions everywhere. Then other mysterious things appear. And so from a practical point of view, yes, we use the sample data systems, we use them, and we try to do this kind of modeling, but sometimes it's of interest to get a better insight of the physics behind. So now we try to go away a little bit from this pure black box approach. Pure black box means you do not know anything. Now we want to go step by step towards something which is a little bit more white. So black and white gives gray, which means that we're trying to discover some properties out of data. This is really an important thing today. So also in control engineering, not just in the AI community, but also for us. You have a collection of data and you want to discover physical properties out of them. That's one of the interesting facts. So, and we want to do this step by step. And the first thing we can do as control engineers, we can start with, instead of using just the sample data and nothing else, we can use our control engineering knowledge, like observability properties and controllability properties, which we well know from multivariable control theory, you learned in one of the of your lectures, and we can use that. Second step would be, well, why not using the continuous time systems directly? There might be something which discovers the continuous time system. The argument behind that is, well, today we have such a super fast sampling process. So why not, and why not discarding the sampling process itself and regarding the sample data system as a continuous value stream? Well, approximately this is more or less true. So why not doing that and trying to identify or to get the continuous time system right out of the data might be interesting, because the continuous time system, if you remember that, is very much more related to what you know from physics. So this is perhaps one perspective. And the last one is, if you remember our discussion from in Port Hamiltonian systems, but also in the principle of least action, you remember physics is governed by a principle of least action. And is it possible to discover out of data this kind of principle? So the performance index, that's the question. Is it possible to capture the performance index if you have data? I will motivate this later on a little bit more. So these are three perspectives, how to get a little bit more physically interpretation into what we are doing. There is what I can also say, there is a complete different branch which tries to bring physics into what we identify into the structure. So particularly, if you remember our neural networks from last time, which you can also say, well, it's perhaps a good idea not to allow the neural network to train everything, where, for example, the Newton's laws are not fulfilled, because, well, if you just look at the pure neural network, it's clear that Newton is not fulfilled a priori. So it's perhaps interesting to just look at neural networks which fulfill Newton's laws. And there's an interesting fact, because if you talk to the computer engineering guys, they very often say, yeah, we're doing this for data efficiency. We're working in just a subspace of the entire possibilities and try to reduce the number of searches if you have these super large neural networks. So these are physically inspired networks, which are also ongoing current research. Makes sense. So for me, plays an important role to say that the data can only behave, that your models can only behave the way physics allows. So we are using these models on Earth and not somewhere else, and so it makes sense to have some sort of physics inside. So this is a complete different branch. It's ongoing research and not yet ready for lectures, in particular introductory lectures. But these parts here I present. The first two are, or three if you like, well known already, and the last is ongoing research, and I just present it as some sort of advertisement of our institute because we are working in this area, and therefore it's called Outlook in that sense. Well, we start with still a discrete time setting, but now we want to apply some knowledge from our control engineering practice. And well, here as a motivation again, well, discrete time models do not allow a link to physics. This is somehow difficult. Therefore, we should use models which are interpretable, and therefore we apply or we look up for continuous time systems or other identification methods, which are presented right now. So, and the learning outcomes for the next two lectures in particular, or three, let's see, are more or less the following ones. You should know something about these physically interpretable models and how this can be done using these procedures I will present to you. It's necessary that you can apply these methods to very simple systems, because remember, well, in our oral exam, we just do simple systems, but tricky. Yeah, it's always the case. Just simple example, but tricky. Simple means small. Because the huge ones are, well, up to the computer. Okay. And know the basic principles, what happens with the disturbances, etc. So all the things we did before in the database part of chapter 5. Okay. So, and the first step is, well, not completely interpretable, because I just want to say we use some sort of knowledge of our control engineering practice. We know something about observability of a system, and the subspace identification method, well, is somehow intermediate. I could have placed this method also in chapter 5. It's also possible, but it's also good to have it here in chapter 6. So it's always a debate with my research assistants whether it's better chapter 5 or 6. So, well, I choose 6. It's called subspace identification, and it's also very old and traditional technique, which has already been invented by Kronecker for a complete different topic, but Kronecker showed that there's some representations can be done to represent data in a certain way, and these are used here. But later in the 90s, the very early ideas by Kronecker have been reused for system identification, and the so-called subspace identification method popped out. And why it's called subspace is something you should know afterwards. Why is it a subspace? What is different to what we have done so far? And what are the main ingredients? So more or less. It's a method which is used today in practice. Okay. Well, first of all, and this is my main message, if you compare the IV method, so instrumental variable method, or even the least squares method for system identification for linear time invariant discrete time systems of chapter 5, was more or less a one-step procedure, right? So you have your data, you take your data, put it in your Muir-Penrose pseudo-inverse, and you get your model parameters, right? That's the procedure we learned. So it's one step. Taking data, Muir-Penrose pseudo-inverse, and we are happy. So just some calculations in between, but it's one entire step. Well, this is perhaps not the best thing, and you learned that already in the IV method. Sometimes it's perhaps helpful to look at the data somehow differently, so from a different perspective. And if you remember the IV methods, the instrumental variable method, there we use some sort of coordinate change with the W values to transfer the data, the output variables, as well as the input variables and parameters in a complete different perspective, so new coordinate basis, and then we were able to get better results for our identification. Better means in this case we get hopefully consistent estimates. The subspace identification is completely different in that sense because completely different to the one-step procedure. It represents the data first differently in a certain setting. And the main problem in between, or the main thing in between, is a subspace revealing matrix. What it is, we talk about in a second. So we have some intermediate step which just rearranges the data differently. And with this rearrangement, we can look at the problem a little bit better than before. And with this rearrangement, we are able to identify a specific model. This is different. Second, what is different? Subspace identification directly targets the state space system, not the input-output realization by means of a transfer function. So we are looking at an input-output state space system. So what is our target? If you remember in discrete time, by the way, if you remember your lectures in multivariable control, xk plus 1 is equal to a times xk plus b times uk, and yk is equal to c times xk plus d uk if there is a direct feed through. So what are the model parameters? All entries in the matrix A, B, C, and D. So it's completely different what Mr. Kluge is doing. He always says, yeah, the name is funny, I think. That's, I told him that, and he laughed quite a lot about his name, but I think it's pronounced that way if he had lived in England or so. So, yeah, and I said, well, it's completely different because he says, okay, you have A, B, C, D. That's my assumption. Let's design a control strategy out of it by pole placement, Ackermann, and whatever you like. So eigenvalue, eigenvector placement strategies, or Riccati control, all these things. But the assumption is A, B, C, D is given. Now we are looking for A, B, C, D based on data. So you have a set of measurements. Of course, it's clear very often you don't have the output, the state values. Of course, you just have input and output, and states are just an intermediate thing. Yeah. So something which are describing the states are describing your system, as you know from your chapter 3, 2, and 4. But so we have just input-output measurements, and we do something in between. We calculate a so-called subspace matrix, which helps to discover then the state space realization, a state space model. So perhaps we can write it down. It's our state space model realization. It's a state space model. So, sorry. Put this in brackets. And this is different. These two-step procedure instead of having a one-step procedure in saying the squares estimation. Okay, so let's start with our setting. Here are the state space system. Xk plus 1 is equal to Ax plus Bu, and Y is equal to Cx plus Du. Of course, discrete time is set. Well, what we can do now is, if we want to describe what the data, we have to look at the output, because we can just measure the output. No? We have output measurements. So let's use the state space model. Suppose the model is given to predict the output. Something Mr. Kluge already did in this lecture. So we can say we send the state space model into the future, which leads to the following thing. We can build yk plus 1, yk plus 2, and so on until yk plus j. So it's just repetitively inserting the state space model in the state space model in the state space model, and so on. And we end up with the following nice structure. We get Cx, k plus 1, and then I insert the things. So xk plus 1 is given here. I insert it, expand the expression, get Cax plus Cbu plus duk plus du. Next step, the very same. I can use this one, Ca(xk) plus 1, etc., 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 and I end up with this one. So with all of these, for a specific k plus j term, you see the structure already here in the just repetitively inserting everything. It looks like this. We get Ca to the power of j times xk plus something which collects all the terms which are given by u, uk plus, k plus 1, uk plus 2, etc. So it's given here. Now I do the following trick. I staple everything in a one big vector, so to describe y in the steps yk plus 1, yk plus 2, etc. And I end up with the following thing, which is given here. And you see here Ca squared, Ca to the power of 3, until I end up with Ca to the power of j times xk. And then a specific matrix which includes all the entries here. And if j is equal to 1, obviously this disappears. It becomes quite simple. So we start with D, CB, D, etc., etc. Well, it's clear. Suppose you don't have inputs. Suppose U is equal to 0 and you want to get discover the output from the output the state space, the state variables. That's the question Mr. Klubi's discusses with you. Well, the only thing you have to do is you have to invert C, CA, CAJ, this wonderful matrix here, and that's why it's called observability matrix. I think, well, instead of looking at the continuous time observability problem, the discrete time is quite simple because you get a set of data and you can discover the states based on a sampling of the YK values. And this is the well-known common observability matrix if J goes to N, right? -1. So if we have this, then, and the matrix has full column rank, then we speak of an observable system. And observability means what? Yes. Of every state, and yes. In particular, it's exact that you can get the value of every state, and in particular, observability is defined that way that we want to get the initial state. Right. So, therefore, observability, obviously, if we start with k equal to 0, then we get the initial value. Its observability is completely. It's a sufficient and necessary condition for a linear system that this matrix is invertible at least, or has full column rank. We get a submatrix out of it because C is not a row vector. It's perhaps a entire matrix. So we just need some sort of column rank. Full column rank is necessary. This is interesting. Okay, observability revisited, simply described in discrete time. And the second matrix has also a name. It's called Toeplitz matrix. I don't know whether you have heard this term. It's interesting because it describes the impulse response behavior of the system. For the impulse response, it's more or less what the input does appears somewhere in the outputs, and here you see the states do not play any role, and there you see the behavior from input to the output directly, right? That's therefore it's also interesting. Has also the very values are called also Markovian parameters of the system. Just if you have heard this, to make this connection. Not so important for us here. Okay. Now let's have a deeper look on these two matrices. We have C, we have CA, we have D, we have B. Obviously, these two matrices contain all the information about the parameters we are seeking for, right? So, but unfortunately, so good news. First, the good news. Good news. If we had the matrices Q and H, so J is assumed to be so Q is Qn, J is assumed to be n-1. If we have Q and H, then it should be possible to get the parameters C, B, A, and D, because they are included, more or less. That's the good news. So somewhere in the observability matrix and the Toeplitz matrix, everything is included. So if we have these, we'll be fine. On the other hand, bad news, they are present in pure form except C and D. But all other parameters, A and B, are somehow just multiplicative included. only in a combination C times A to the power of 2, and so we have still the problem. Yes, the matrices are nice, but we are looking for A, B, C, D, and not for the matrices. And there is the intermediate step. First step, try to discover Q and H. Second step, if you have Q and H, try to calculate CABD. First step seems simple. Second step seems complicated. Yes or no? No? Well, first step, let's try. They are basic. We first start with the first step, of course. Always start with the first step in your life. And we try to discover Q and H out of our, in particular Q, because if we have Q, then we have C and A. And with the C and A, we probably get B and D. This might be the way to go. So therefore, our first attempt is to get Q in a sufficiently well way. So first step, Q, calculation of Q. And the question is, how do we get Q out of data? Well, everything we need to know is more or less here. Suppose there are no inputs in the first step. Suppose there are no inputs. Is it possible to discover Q? Because X is also not known. Second bad news. If you have, well, first thing to make it trivial, if X is well known, also measured, you have Y, then you get the observability matrix, right? Seems clearly possible because you just need to invert this matrix. This is a little bit mathematically tricky because it's not a square matrix. It's a little bit more complicated. C is not square. C is a row-wise column matrix. So we have to look at a substructure. Problems or questions? Okay. Substructure out of it. But the basic idea is, it seems simple. So if X is given and Y is given, we get the observability matrix. And with this observability matrix, we would be able to discover C and A and B and D. So we can, but let's put it like this. Okay, so X is unfortunately not given. This is one problem. But there's the second problem. It's not possible to invert the matrix Q directly, right? Because if you, well, second problem is concerned with the question when to stop with J. Or we can also say, if we do not know the order of the system, N, what to do then? And this is a typical setting. We do not know the order of the system. So N is not given. Here are our problems. No N, no X, but Y and U given. That's the setting. Okay, let's start with N. Now you can use your control engineering knowledge. And here, that's why I say, well, it's a little bit closer to the physically informed situation, and therefore it's in chapter 6, because you can use your control engineering knowledge. What do you know about how far you have to go with J if the system is observable. What does the Kalman observability criterion says? Please feel free. Yes. Why not? Yes. Full column rank. Yeah. Can we be sure that we reach the full column rank with j equal to 2 if the system is of order 5? No. Exactly, which we do not know. But what we can do is we can go, well, to any value which is greater than lowercase n, right? So we don't know how far we can go, but we can say, okay, it's less than 50 or less than 100. So you can put everything in the vector yk plus 1, and end with j equal to n, j equal to somewhere, but greater than n. That's something we can do. It's practically possible, right? Well, then there's an interesting fact. If you just look at this part here, the interesting fact is that this matrix and this vector repeats, right? That's part of the proof of the Kalman observability criterion. You just have to end after n minus 1, right? So even if j ends up by 1000, here you will always discover the observability matrix, nothing more. That's the interesting fact. So the states of the system, you just have a certain number of states, say 5, for example. And the observability matrix, it repeats. Let's have a look here. If you enter j, or making j even greater than the order of the system, it repeats. It repeats. That's the interesting fact. That's the very, very important fact Kalman discovered. And this is important because the entire state is in a subspace, and the observability matrix obviously also. You do not get more information about it if you repetitively enter more data. This must be the case because it's obviously here just the observability matrix. The states are limited, the number of states, but also the number of full rank, column rank is limited due to the Kalman criterion, right? So obviously, on the right-hand side, you have something which is limited to a reduced space compared to the left-hand side, where you have your data, which can infinitely often be measured. So you do not get more information out of it because the system is described by a finite number of states. And in addition to that, we know by observability assumption that the observability matrix repeats. Now, this is a little bit homework. Please look in your multivariable control. Proof of the Kalman observability criterion for discrete time systems, because there you will find why it's repetitive, why it's given. very famous theorem by Cayley Hamilton, which is used there. So please look at that so that you understand, okay, the observability matrix repeats, and we are on the right-hand side if we neglect the U values. If we neglect the U values on the right-hand side, we are obviously in a smaller space compared to the left-hand side, right? Because left-hand side, you staple your output values or your vectors, vector, 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 1,000 times. But on the right-hand side, so C, so Q times X must be from the dimension of variables, from the dimension of matrices should be smaller than that, right? So the question is more or less, is it possible to get this subspace, which is more or less responsible for describing the entire dynamics? And the wonderful answer is yes. It's possible. And I want to show you how we do that. First of all, I have to introduce some matrices which are necessary for that. And the first is the so-called past data matrix. It's built by means of the matrices we looked at before, but now we look in the past from a specific time instant K. We look in the past, P steps in the past. So past is here, so I go backwards P steps, okay, P is 3. And second, I look in future vectors. I look in the future, F steps forward, and take this matrix, these output vectors. And then I can produce a matrix, YP, which is defined as follows. I start with K equal to 1, and, K equal to 5 if P is 6. And I go always backwards until the very beginning. Then I fill in the next step, backwards, next step, backwards, next step, backwards. So I have here a matrix with n measurements, for example, and fill an entire matrix. And well, these are my measurements, step by step by step by step, always backwards and always looking one step forward, right? Even more. I do the very same with the future matrix. So it's saying the future data matrix, which we call YF. And I staple the very same, starting from K equal to 6. And therefore having Y7, Y10. And I look in the future. Next is I look here for Y7, 8, 11, etc., etc. So again, I have a huge matrix by rearranging the data. These matrices are interesting because why? I can now look at the same system a couple of times. First, from step K in the future, then from the step K plus 1 in the future, then from the step K plus 2 in the future, etc. And I get always the following interesting fact. We can build this QF because we look future steps in F steps in the future, and then I collect always the things row-wise. Yes, row-wise, sorry. And no, column-wise, I was a little bit okay. So we put here our YF with our measurements column-wise. I get the observability matrix part because F is not yet known. Here I get my states, and at the very end, all the things which belong to UF, right? So it's nothing else than describing the same system from a couple of steps forward in the future and collecting the data. So what do I have? I have the structure I talked about a second ago. On the left-hand side, I have a matrix which collects our measurements. always one step in the future. On the right-hand side, I discover from our physics structure, our control engineering structure, our matrix QF and all the initial states, right? And then I have still the input values with the parameters D, CB, etc., and UF. And the only thing I know is UF. Unfortunately, the matrix HF is unknown. QF is unknown, so we are looking for HF and QF. QF first. And then HF. Okay, so now what we can easily get is perhaps if the states are given, of course, then I get QF. If we can suppress somehow UF, right? So the first step towards this is how do we get rid of UF? That's the first question. And perhaps you remember a very nice trick from our least squares identification chapter 5. It's possible to identify parameters, only a subset of parameters, if we annihilate some parts of the equation, if you remember that. And that's exactly what we're doing. So if xk is known, the problem is easy. Unfortunately, UF is not known. UF is known, but we still have HF. So if we just want to get QF, we want to get a subset of our parameters. And the very simple idea is multiply this extended space with the orthogonal complement of UF from the right. Orthogonal complement means it annihilates UF. UF times the orthogonal complement of UF gives 0. And if I do this from the right, I get rid of the parameters HF. What remains is this matrix here setting, which is given YF times the orthogonal complement of UF, and the right-hand side QF times XK times the orthogonal complement of UF. Okay. Well, so first part of the steps is done, and now here comes the, well, I would say the very important trick. It says that, or you might have heard this, that every matrix can be decomposed in singular values. And so a matrix, which is here on the left-hand side, can be decomposed in this matrix here. It's the same. Can be decomposed in U times S times V. It's perhaps not so wonderful to use U. It's a different U here, right? It's not UF. Well, let's put it like this. Not so good. It is not UF, right? Important. So what singular value decomposition means is you can always decompose under certain mathematical restrictions, of course, but you can decompose a matrix into first the so-called singular values, which are stored in S, which are on the main diagonal. A matrix U, and the matrix V transposed. That's the main setting. You can also say, if it's on the main diagonal, you can say, okay, there are some parts, we can split it into two halves and can say it's US to the power of a half, and S to the power of a half gives 1, of course, V transpose. To make it explicit, it looks, these matrices S look like this. Example, S may look like 1, 5, and zeros here. So obviously you can decompose it into two square roots. That's the main setting. And now the trick is to say, okay, we have to decide which part belongs to QF and which part belongs to XK times pi UF orthogonal. And this is by choice. We say, okay, because the left-hand side is given, okay? Left-hand side is given. You can split the left-hand side into these two parts, and the association is that you say, okay, this part here, the first part, belongs to QF, and the second part is XK times pi. I omit here pi UF, not to forget orthogonal, of course. So with that, we can say, okay, well, if we do the singular value decomposition, I get QF, and with QF, I'm happy I have QF. Good idea. So what are the steps to be done? You fill in a matrix YF, which is just sample data. Back to our structure here, YF is given. It's just this structure here. You fill in data. You take this matrix, this super matrix YF with all your sample data. You make a singular value decomposition. And the singular value decomposition somehow decomposes all the things which are representative for the system structure. And with the singular value decomposition, you can say, okay, the first part belongs to QF, the observability matrix, and the second part to the states. That's the basic idea. Now, this is only the first problem. We solved, okay, QF is given. In a similar way, you can also, by the way, define HF. I just want to give you the basic idea of subspace identification, right? But now, what if we have QF, what can we do with that? Now, the second problem appears because we have to decide or we have to discover, we have to calculate the values of C and A out of QF. Well, this is simple. Why? Because you can look at QF at two different time instances. Now again, we use some nice property of the observability matrix, because if you have an observability matrix or a submatrix of the observability matrix, if you multiply the observability matrix again with A, you get the next one, right? Next row. And we can use this information. So first, C is easily discovered out of QF because I have just to look, well, I know the number of measurements because I have a number of sensors. I look in the first 5 rows because I have 5 sensors. I know C. Okay, so back to sorry, here. back to this equation. Yeah. So if I look at the first QF entry, first entries of QF, I have C. Second, I can look at two matrices, namely Q1 and Q2, without C. Obviously, we get Q2 out of Q1 by multiplying with A. So if C is given, I get A out of the following equation. I just have to calculate A, being a matrix. Q1 is times A gives Q2, so I have to invert Q1 and get Q2, times Q2, and I have it. Due to the fact that it's overdetermined problem, we have a least squares problem, we solve the least squares problem. And then we have A. So now C and A are given. And that's where I want to stop. Of course, you can imagine same if you get HF in a similar way, because you annihilate X, then you get D out of HF, and CB, C is given, D is then given. You again have a least squares problem to get B. So with such a kind of procedure, you're capable to calculate A, B, C, D. And in addition, and that's the funny thing, by means of the singular value decomposition, you will see, you might have asked, well, it's nice, but YF is perhaps a huge super matrix. On the right-hand side, there must also be a huge super matrix. Where is the subspace of states we are just interested in? Well, this happens to the fact that in this super matrix, if you look at the singular values, some of the entries on the diagonal are 0 or almost 0, close to 0. So you can see by singular value decomposition, you can see QF, you can see the number of states. This is something hopefully you will do in the exercise lecture and see, well, do you adjust the singular value decomposition with a simple system? Also homework. Try it, enter some values in a state space system, write down some matrix A, B, C, D, enter some initial values, do some calculations, take these values, and then you will see some of the values will collapse and you just get the perfect number of states. That's it. So what I wanted to say, okay, that's what I wanted to say. So very easy. We have two basic, if we want to talk about what is different to least squares problems, first of all, we have two steps. We have an intermediate step. This intermediate step discovers first the observability matrix and the triplets matrix. Second step is we try to recalculate A, B, C, D out of these two matrices. So two-step procedure. Second, we need the control systems properties like observability. Without it, wouldn't be possible. Third, in addition to what we have in discrete time case for least squares problems, we get the order of the system directly, right? And so we get order information. That's the interesting fact because of the number of entries of A, B, C, D. This is in contrast to what we know from the least squares identification problem, because in the least squares identification problem, IV method, if you like, we have an assumption besides linearity, important. We have to define what is the order of the system, because we have to write down the number of parameters which we want to identify. If we don't do that, we will have a problem. So, wonderful method, works in practice also very well. It's also used and also implemented. So if you look at computer-aided design tools, this kind of calculations are implemented. Well, where are the problems? Let's talk about that. So first of all, if you have some sort of disturbances, you can imagine that it's not perfectly exactly the number of states you get. So you have to decide somewhere where to discard something, like the number of rows. That's one thing. Second, well, it's a little bit mysterious for me. It's still today to say, okay, why is this choice a good choice here in between? Well, one can say it's. I wrote here a balanced choice is a good choice, more or less. Balance means that you split it into parts, and the first, and we can assume that the multiplication here is more on the right hand side is also somehow can split into these two halves. Makes sense, but is not formally justified. So it's just a choice. Okay, there by the way other choices which also work well. What you can prove is the choice is somehow compatible with state transformations. So if you look at differently at the state, so that's not the problem. But that's all. So there's nothing more to justify this at that point. Okay. Well, second procedure for identifying a system. Now we get a state space system out of it, and yeah. I added also a subspace identification case with stochastics. I don't want to go into details here. It's also not part of the story of the exam, but if there's somebody interested in that, he will also nicely see there's a connection to the Kalman filter at that point. So somehow we find something similar, like the Kalman filter, if you do the subspace identification towards that. And I found it interesting, and therefore I put it in the slides for your later use if you do subspace identification in your daily work, perhaps. And you're wondering why do I get the similar things, or a colleague is saying, hey, why not a Kalman filter? And you can say, hey, it's the very same thing or similar or something. You find it here. Okay. Some issues. Well, this is the first part. And now I want to go to, well, it's still a discrete time setting. We still have a discrete time state space representation. Well, let's put it like this. It's not physics, obviously. It's still discrete time. The only thing we used is observability matrices and some properties from control engineering. Now we want to directly jump into the continuous time case. And first of all, I want to give you a simple example and ask why not doing it this way? Why all these difficulties in calculating the discrete time things, etc. And why not keeping the problem simple? And this is a question which is really interesting to talk about, because when the continuous time problem started to appear, it was in the 60s, 70s already, last century. Then everybody realized, well, it wouldn't work because we just we have a sample data system in practice, we cannot sample sufficiently fast. It's a problem. Then they disappear completely in literature. And well, over the last, I would say, 20 years, 10 years again, they appeared again because analog digital converters became so fast. So it's also interesting to know from a historical point of view, perhaps. Well, simple. We want to look at a simple example, and I want to ask some questions which might explain the need for a new procedure. So suppose we have the following setting. It's a continuous time system, and our aim is to calculate A and B based on measurements of U t and y of t. So you have a value stream U of t and y of t, and you want to calculate A and B. So my initial idea would be the following. We'll take two measurements. U of t0, U of t1, Y of t0, and Y of t1, and put everything in our equation. And the very same for the time instance t1. Well, a choice, we can rewrite this equation in the following form. We can also write it down as follows. Why not doing it this way? Y of t0 minus y dot of t0 and U of t1 minus y dot of t1. Sorry, it's a matrix. I was a little mistaken here. Minus. Multiply everything with A and B. And the right-hand side, we write down the following thing. Well, then this is a matrix L. Our parameter is theta. Our output Y. And finish, invert L. You get theta. That's it. You may ask, hey, why didn't you tell us this simple trick at the very beginning of the lecture? What's the problem with that? It's so simple, isn't it? We get A and B out of this simple equation, two equations, two variables. Simple. Yes, of course, practically, but this problem is always present. So something else. But you're right, of course, if the system equations do not match, well, then our crazy new idea would be take 50 measurements T0, T1, T2, T3, T4, etc., and write it down. You get a super matrix. You do your Penrose pseudo inverse, and you get the very same results. Hopefully, you smooth it out. Your problem might be also problematic. There's perhaps a problem with y dot. What's about it's if you ask a mathematician, he would say, no problem at all. It's simple. I do it that way. What's the problem with y dot? Because you have just measurements y of t and u of t. No measurements of y dot. Why is y dot a problem in many practical applications? Any idea? Yes? Mm-hmm. So I try to do my very best to depict your atypical measurement. So if you now we assume T0 and T1 are close by. Well, if you look at this curve, you might say, well, it looks like a sine function, right? Because your eye is smoothing out all this nice properties like these fluctuations. And you would say, okay, it's a sine, the derivative of it would be a cosine, so simple. What you are doing is you look at the entire function, you have an entire picture, you do signal processing because you heard lectures about signal processing already. But if you have just these two measurements, just to explain what I mean, the derivative would be a cosine. Hopefully I put it right here, would look like this. So at this point, perhaps I put it in different color. This would be perhaps the derivative, but what you are doing is calculating this one, which is obviously completely wrong. So if this works, so put it positive. If you have noiseless measurements, and if you have only one derivative, like in this first order like element, then no problem, do it as shown before. If you have noisy measurements, so fluctuations, white noise, whatever you like, then your derivative calculation becomes the most important part of this procedure, right? So what can you do if you want to do the calculation of the derivative of a noisy measured signal? Noisy signal, I would want to say. Yes. Yes. So we do some sort of low pass filtering. What is the problem with low pass filtering then? Yes. That's the problem. So it delays. So your derivative does not belong to your time instant you want to calculate a derivative, but to another time instant, because if you a simple low pass filter shifts the signal a little bit towards to the right, and therefore you get some sort of delayed information, and therefore the time derivatives do not instantaneously match your measurements. So what can you do about that? This is the engineering way, by the way, what we are doing right now. Suppose you know the delay. Exactly. We can shift the signal again, and that's one way we can do it. So filter the signals such that you're happy with the noise level. Be careful with the delays you enter there. So not just filter the signals, please filter everything. That's the second way you can do it. Filter both signals, so everything is in the same time range again. And then be careful with the results because they are based on delayed signals. If you have huge noise levels, would be problematic. Second remark, but this would work, of course. Second remark would be, sometimes your systems are not of order 1, but of order 2, 3, 4, 5, which means 5 times a derivative of a signal. Please do that at home with Simulink. Third homework. Sorry for that today. Take a Simulink block, signal input, like binary, what kind of noise you like. If there is sources existing, then take a first order derivative, second order derivative, third, and then look in the scope what happens. It's not nice. That's something I can tell you. But, well, I have another idea, which looks like this. Remember your equation, which is here on the top. U of t is equal to y of t plus b u dot of t. Why not integrating the equation? Looks good, isn't it? No derivatives at all. I integrate the equation. So we do the following. So A instead. So perhaps it's the green way. A, and then the integral u of t dt equals the integral. The equation is still correct, right? Dt plus b, the integral of u dot of t dt. This is an integration I can do. So we end up with y of t and the integrals. Of course, we have to define some range, perhaps t1, t0, t1. So we use the entire information which is given in the signal, right? Now you might say, okay, t0 and t1, if they are close by, then I do not integrate anything, because if the integral, if the interval is too small, the original equation remains. But if you have t0, t1 a little bit distanced, then this would work. What do you do then? You use your information of the entire signal, right? That's the way it goes. And this also works with 2 derivatives, 3, 4. This is the good news. The bad news is you have to integrate 2 times, 3 times, 4 times, right? But it works. So you get this kind of equation instead of the original one. And the question is, can we formalize this idea? And can we use it in a formalized way? And the answer is yes. It's called algebraic method. And I tell you why it's called algebraic method, because it easily works with so-called the well-known and very famous and very loved Laplace transform. Because you can do the integration in the Laplace domain, of course, and then do some nice things in the Laplace domain. It helps you to do the calculation. You can do it also directly with integrals, but for me, it's easier to do it that way. And I want to show you this for this simple example, and then show the entire procedure. And I also want to show that you can get rid of some constant disturbances in your equations. And this works quite well. So doing the very same, instead of the equation I presented, please look at the following fact that I have here a disturbance which is present. See, sigma of t is a constant which is added, and we do not know the constant itself, so the height of the constant disturbance. So we have a biased situation. So this is some sort of disturbance, which is unknown. Okay. Well, first of all, to make this things a little bit simple, I assume that the initial values are 0. Of course, it works with initial values. You will see it, but at the first glance, we think the initial values are 0 and assume that, and then we do the Laplace transforms. That is something of the Bechner degree. You get I US minus SB U Y of S plus C over S. That's nothing mysterious about. Now, we use something which you might have learned during your signals and systems lectures, a trick which works in Laplace domain very well, but also in how it's called chi, I think, complex analysis, integral transform. You learn something like the derivative of a Laplace function. You never used it. Here it comes. Here you can use it. Well, what happens if first I multiply this equation by S? I get C on the right hand side here, and all the other equations remain more or less the same, but multiplied with S. And then I do a derivative in Laplace domain. C disappears. Well, I get the following: y of S times, I have to be careful. I have to apply the product rule because I have S and y of S. So first, S derived gives 1 times y of S plus S not derived, but y of S derived. So we have the derivative in Laplace domain. Horrible at the first glance, but yeah, it is as it is. We have the wonderful thing is that C disappeared, so we have no disturbance at all. That's it. So this is our equation, and now we use this equation at the very end. We end up with this equation here, and now we want to avoid derivatives in the time domain. So I again do a multiplication with 1 over S squared, because 1 over S squared is 2 times an integral, right? And I end up with the following expression. And now, well, 1 over S squared y of S is something you can do by your own and say, okay, this is 2 times the integral of y of t. Now this wonderful candidate has to be looked at. This is something which you can look in your lecture on signals and systems, that the derivative of y of S gives minus t y of t integrated. And the very same applies here, bless you, applies there and there and there, because this nice rule helps us to do the calculation. So the derivative of a Laplace transformed variable behaves the following way. This is wonderful because now you have an equation with a substantial amount of integrals, but your disturbance disappeared. The bias is gone. And now I rearrange everything in the same way I did before with the y dot story. On the left-hand side, I collect all the y values, define the z vector. On the right-hand side, the u values, and some combination of u and y, and with the parameters a and b. So I have an equation is z is equal to m times theta. This is something we know, so we invert m and get the parameters a and b. Easy. And no derivatives at all, just integrals. And no delays, just integrals. And it works that well. And in addition, just I try to promote this a little bit. In addition, we can completely discard the bias from the equation. C is not known, so it's gone. Wonderful, isn't it? Constant disturbance disappeared. Yes, it works as it is. Wonderful. So why, what are the problems? So always, we are at university, it's not just promoting, it's not always good. So here are the downsides. Well, first of all, we have to calculate the integrals. There we are. In this sense, the integrals here are not completely defined because I have not said something about the, first I forgot something. Till here, sorry, I have just one equation. Just one equation. This was my first equation. I integrated everything. I ended up with one equation because I have just one system equation. Well, if I want to get two parameters out of one equation, this won't work. I need at least two. So it's necessary to get two equations, at least. One way of doing it, integrate it another time. And you would say, it's crazy, man. Please, I hate integrating functions, and then I have to integrate once more. But integration plays a role. What do I have to do? So practically, I have to integrate my measured signal. So I have measurements. I have to integrate it twice or once, multiply it with time. Possible, I think. Well, numerical integration is easy, isn't it? It's like, well, for me, it's like building blocks. So block per block per block. It's adding the sums. It's integration. That's it. So numerical integration, quadrature, we learn in numerics perhaps formalisms, how to integrate numerically with data. You can apply this. Of course, you have to define in which interval you have to integrate. Therefore, this equation set is not complete. We have to define the integration interval. So from T0 to T1, perhaps. And so on. Well, if we do so, we have to do this specific integrations using numerical integration. You know, that's possible. A computer can do this. You have the signals, you integrate the signals, you integrate it a couple of times. That's it. There's a second way to generate a second equation. The second way to generate this equation is based on looking at different time intervals. Well, T0 to T1, T1 to T2. Also possible. You can also look at 3 time intervals, 4, 5, 6, 7. Then instead of having here a matrix M, which is in this case a 2 by 2 matrix, you end up with a row matrix, of course, because you have more equations than parameters, and then you can apply your wonderful Penrose pseudo-inverse. That's why we learned this again in the chapter 5. So with that in our hands, we end up with a simple procedure. And there's one question left, and this is something I ask you for our next lecture. Well, could we be happy with the result? First question we answer now, and second is for you at home. The more difficult is for at home. The first question is, well, how do we define that we are happy? Well, besides good weather and things here in this identification problem. In system identification, under which condition should we be happy? Yes. Yeah, and under which condition we define that something is correct? Yes, more formally. So we had a definition. So if the parameters match the parameters given, then we are happy, of course. But is this sufficient? Do we need something else? In particular, if we have not just 2 measurements, but say 50 intervals, for example. We talked a lot about this in chapter 5, to give you a hint. Exactly. And now there's the question. Suppose you have not just 2 parameters, because there is nothing more that you can do than inverting the matrix, but you can ask the question, suppose you have Y measurements which are noisy. You have added noise, white noise, for example. And well, due to the fact that you know that you have noisy output measurements, non-noisy input measurements, for example. You make, well, say, not just 2 equations, but 50. Do you get a consistent estimation of A and B? That's the question for next time. The only thing I want that you bring together the knowledge from chapter 5 with the problem here. Next time we will talk about what we can do about that question. So the question again, is it consistent? And please use your knowledge from chapter 5 there. That's it. Have a good day. And yeah, see you next week. Tomorrow, I think we have exercise lecture, I think. So bye-bye.